we've come across a lot of functions in this entire semester, but we've never defined a function. Now, finally, in this chapter, we're going to define a function formally, and we will discuss two important functions. That is, um, the linear function and the exponential function, and how certain real world situations can be modeled using these two types of functions. Now let's start with an example. Every year, Jake's salary increases by a fixed amount of $1,000. His present salary is $55,000, and the maximum that his salary can be is $95,000, which means if he reaches the $95,000 mark, then his salary stops increasing. So, what are the variables in this particular situation? The two variables are the salary, which depends on the time. So, the time in years is a variable, and the salary is another variable. So, the salary, that is Jake's salary, depends on the time. So, the dependent variable, which is usually denoted by y in math, is the salary, and the time is the independent variable. So as time changes, or as time increases, Jake's salary increases. That is the rough description of the relationship between the two variables, time and salary. So in the year one, or in the year zero, at the beginning of this whole process, his salary is $55,000 plus nothing, because 0 times 1,000 is 0. And we're writing it as 0 times 1,000, as you can see a little later only, just to establish a pattern. Once we establish a pattern, we would be able to model this particular situation using an equation. So in the first year, there is an increment of $1,000 in his salary. So it's his base, which is 55, his initial salary, which is $55,000, plus $1,000, which is $56,000. So in year one, his salary becomes $56,000. In the second year, so now 2 years have passed by. For every year, he gets an increase of $1,000. So in 2 years, it would have to be 2 times $1,000, which is $2,000, and that is added on to 55,000, which makes it a $57,000. So in the third year, following the same pattern, there are 3 increments of $1,000 in 3 years. So every year there's an increment of $1,000. So it's 3 times $1,000. That is the increase from the beginning, or the initial value of his salary, which is $55,000. And in year 3, his salary is $58,000. So the pattern continues. So once we establish the pattern, we can figure out his salary in any one year. So in year 10, for example, we don't have to go through all the steps. Now we know the pattern. So it would be $55,000, which is his beginning salary, plus 10 times $1,000, because there are 10 increments in 10 years of $1,000 each, so which makes it $10,000 plus $55,000, which is $65,000. So we can pick any one year and figure out what his salary is. So generalizing, if we say his salary is Y and the number of years, which is the independent variable, is X, we can model this relationship between salary and time using the equation Y equals $55,000 plus 1,000 times X dollars. So this is an equation that represents the relationship between X and Y. We call it a function because, if you recall, the definition of a function is the relationship between two variables X and Y, where x is the independent variable and y is the dependent variable. If it's a function, if for every x there is exactly one y. So if for every x there is exactly one y, then we say that it is a function. So let's check if this is a function. We know it's a relationship between the two. Let's see if it's a function. So if I plug in an x, is there any way I can get two values for y? That's impossible. If I plug in an x, I enter it into my calculator, I get only one answer. So for every x, there's exactly one y, and therefore it is a function. So that is how a function is defined, and that's how you can check if an equation represents a function. So once we know what a function is, we need to know two terms or two definitions, that is domain and range. So what is the definition of domain? Let's look at what the meaning of domain is. Domain is the set of all possible values of x. Now, we know that the minimum value of x is 0. So that is the beginning of time. So time t equals 0. Now, the maximum that the time x can be is 40 because y equals 55,000 plus 40 times 1,000 is equal to 95,000. So in 40 years, his salary is going to become $95,000. After which, this model that we've set up is not going to work because there will not be increments of $1,000 after 40 years. His salary is going to be a maximum of $95,000 and then it stops growing. So 40 can be a maximum, but to be really precise, it's better to write it as 0, 1, 2, dot, 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 40. Because this might give us the impression that x can be any value between, let's say, any number between 0 and 40. It could be 3.25 or 39.17. That is not allowed because the years we're going to count only in whole numbers. Now, what are the possible values of y? And again, let's not use this because it gives the wrong impression that y can be any number between the two. So let's look at the values that y can take. The smallest value is $55,000. The next step is going to be an increase of $1,000, so that's $56,000. The next step, 57, and it goes on that way. And the final value that your salary can, or Jake's salary can be, is $95,000. After which his salary stops growing. So that is the definition of domain and range. All possible values of x is the domain, all possible values of y is the range. Remember that x is the independent variable and y is the dependent variable. And then the function that we set up is a straight line. And you may recognize this. If the exponent on y is 1, the exponent on x is 1, then it's a straight line. It's a linear function. However, a linear function is defined for all values of x. It can be any real number, including decimals, fractions, radical expressions, and anything. So here, by defining the domain and the range to this particular situation, we are saying exactly what function we are talking about. So here is what a function is. It's the relationship between two variables, the independent variable, which we call x, and the dependent variable, which is called y. So this is called an ordered pair, where the first number represents x, the independent variable, and the second number represents y, the dependent variable. Now, the notation that we use for a function is y equals f of x. You must have come across this notation in an algebra class. So if we plug in a value of x into the function, we get a value for y, and this is the representation of the function. Remember, the definition of a function is for every x, there is exactly one y. So let me give you an example of where that doesn't happen. Now, we come across many equations where you plug in an x, you get exactly one y. So let's say we have an equation, y squared equals x. Okay, so let's try to figure out, so what is y when x is equal to 1? So we plug in an x equals 1, so we get y squared equals 1. Now we need to figure out y, so I try to plug in different numbers, and I know that 1 squared equals 1. I try to plug in different numbers for y. So 1 squared equals 1. So if y is equal to 1, the equation works. Now, what about negative 1? What if y is negative 1 and I square it? I still get 1. The equation still works. So what are the values of y? It is equal to plus 1 or minus 1. So there are two different values of y for x equals 1. So for any one x equals 1, the y's that is related to is positive 1 and negative 1. So this is not a function, because for every x, we need exactly one y, and we found an example of where x, a particular x, has two different values of y. So this is definitely not a function. And I think you get it. It's not a function. So let's look at some real world situations of two variables that are related, age and shoe size. And notice that this is written in the form of an ordered pair. And in an ordered pair, x is the independent variable comes first and y, the dependent variable, comes next. So clearly, shoe size, which is the dependent variable, depends on age. So as the child grows or as the age increases, the shoe size also increases. And once the child is fully grown, the shoe size remains a constant. So that is how we describe the relationship between age and shoe size. Now, in the second example, time and price of a Ford station wagon. So the price of a Ford station wagon, which is the dependent variable, depends on time, which is the independent variable. So as time increases, the price of the Ford station wagon has increased, starting from the years 1970 to 2015. So as time increases, the price of the wagon increases. So that is a clear relationship. Travel time from Denver to Chicago, let's treat it as the independent variable. The average speed of the car, the dependent variable. So as travel time from Denver to Chicago increases, so you're taking longer to reach Chicago from Denver, you can assume that the average speed of the car decreases. As the car goes slower, the time it takes to reach the destination is longer. Or we can also define it as travel time from Denver to Chicago decreases, which means you're taking a shorter time to reach your destination, then the average speed of the car obviously has increased, so it increases. And once you reach your destination, the speed would have to be zero, obviously. You assume that you stop. Now we've discussed domain and range of a function. The domain is all possible values of x, and the range is all possible values of y. This is independent variable, and this is the dependent variable.